In this lesson, we're going to be learning about the last type of conic section. And it turns out that this conic section is much different, not only in its shape, but also in its equation and its features than the other three conic sections, being the circle, ellipse, and hyperbola. Now here we have a parabola, and we can remember that this is actually the curve that was formed by a quadratic function. But we're going to see things from a different perspective now, where a parabola is the set of all points that are equally distant from a point inside the parabola, referred to as the focus, as it is from a fixed line outside of the parabola, which we refer to as the directrix. So you should realize that the vertex is a point on the parabola. It's actually the lowest or the lowest spot, or the spot where the graph will turn. And we'll see that this point is equally distant from a point inside of the parabola called the focus as it is to a line that's on the outside of the parabola, referred to as the directrix. And that distance is called P. Now, P will actually show up in the formula for or the equation for a parabola. So that's going to be an important distance to take a look at. But it turns out that any point you pick on the parabola will be the same distance from the focus as it is from the directrix. Or in other words, this D1 will equal D2. Even if we pick some other point on the parabola, the distance from that point to the focus will be the same as that point to the directrix. This is the actual definition of a parabola, but what we're going to do now is figure out how can we find all of the important features of this graph and what do the equations look like. So the first thing we should recognize is that a parabola is nothing more than the graph of a quadratic function, which, remember, as a trinomial was in the form y equals ax squared plus bx plus c. Now this was a quadratic function, and we refer to this here as expanded form. But when we look at this from the perspective of a conic section, we're going to want the form to look a little different. So this is referred to as standard form. And standard form will actually have h and k being the vertex of the parabola, while a is going to tell us something about the steepness of the graph. Now we should also recognize that parabolas could open left and right. And if they did open left and right, then all that would mean is that the x and y coordinates have now flipped roles. So a parabola opening upwards or downwards would have the x component being squared, or in standard form, you'd see the whole quantity of x as the squared quantity. While a parabola opening left and right, although it won't yield a function because it doesn't pass the vertical line test, it is still possible to have that parabola, and now you could see that the y quantity is being squared. Now, we can tell which direction it's going to open simply based off of the coefficient called a. So this coefficient that comes on the other side of the equal sign, notice how the squared quantity should be on the left in standard form. If we notice that the parabola is opening up and down, and the a value is negative, then we can tell that it's going to open downward, while if a is positive, we know it'll open upwards. Now, on the other hand, if y is the quantity being squared, we know it opens either left or right along the x direction, the x-axis. And so if a is negative, we know it opens to the left. And if a is positive, we know it'll open to the right. Now, for example, if we wanted to find the vertex and the axis of symmetry of this particular equation, the first thing we should recognize is that because this is y is being squared, we know that it opens left or right. And because the coefficient is positive, we know that it's going to be a parabola opening towards the right. Now, in order to turn it into this standard form, we need to complete the square. So this is where we can now factor out the 2. And now we're left with y squared minus 6y. Now remember that constant just pulls to the outside. This is where we're now going to add half of negative 6 which is negative 3 squared. But notice that if we've added this quantity of 9, we have to compensate by subtracting 9. But notice, since 2 times that 9 is equal to 18, we have to now subtract 18 from the same side. Which now means that the coefficient is still 2, but this parentheses can now simplify to become y minus 3 quantity squared, while 17 minus 18 becomes minus 1. Now this form right here is not actually standard form because the squared quantity is not alone. So my goal here is to get y minus 3 quantity squared by itself. So the first thing we should do is we should add 1 to the other side. But notice the y minus 3 quantity squared needs to be alone, so we need to divide by 2, which is the same thing as multiplying the left side by 1/2. So we can now rewrite this as y minus 3 quantity squared, which is in the form y minus k quantity squared, equals 1/2 times x plus 1. In other words, a is 1/2, which is still positive, therefore it opens right. And now we have x minus h. Now notice that at this point we could find our vertex, which is simply hk, just like all the other conic sections. We could see that the x coordinate of the vertex will be negative 1, while the y coordinate of the vertex will be positive 3. So this is our vertex that has an x coordinate at negative 1 and a y coordinate at 3. Now what we should recognize as well is, in order to find the axis of symmetry, we need to realize that if the parabola opens right, then the axis of symmetry will be horizontal. Horizontal lines look like y equals a number, so the axis of symmetry will be the y value of the vertex, and therefore y equals 3. So we'd like to take a little bit deeper dive into the equation of a parabola by taking a look at what a parabola looks like and what the important features actually are. Now, as we saw on the previous slide, the form could be different depending on whether or not it opens up or down, because x is being squared, while over here, y is being squared, and therefore it opens right or left. Now notice that in this case, the vertex is going to be the hk point, and the axis of symmetry will cut the parabola in half horizontally, in this case because it does open right. Now there is an important point that lies inside of the parabola referred to as the focus. And this value of a in standard form will tell us how much the graph stretches in order to create some new shape, some new form. Well, the important part about this a value is that this coefficient called a is equal to 4 times p, where p describes the distance from the vertex that we should know, hk, to the focus. So, for instance, if the a value happens to be 12, then that means that 4p is equal to 12. And if 4p is equal to 12, then that means that the p value would be 3, and therefore the focus would be 3 units away from the vertex. Now, the great thing about this as well is that the directrix, or the line on the outside of the parabola, it's always going to be perpendicular to the axis of symmetry, and it will also be the same distance from the vertex as the focus is. So if all we know is p, we could find these two important features of the graph, namely the focus, which is p units from the vertex, and the directrix, which is also p units from the vertex. Now, if the parabola opened up or down, we would realize that the directrix would be horizontal because the axis of symmetry would be vertical. I encourage you to draw a rough sketch to see why that would be. Now, remember that we learned a property of parabolas that said for any point that we choose on the parabola, the distance to the focus will always be equal to the distance to the directrix. Now, what if we pick the point that's parallel to the directrix and straight up from the focus? What if we'd like to find this blue point that's straight up from the focus. Well, what we should recognize is that D2 is the same distance as the distance down here from the focus to the directrix. So that means that the distance from this blue point is 2p units from the directrix, which also means that this distance here is 2p units. And therefore, to the opposite side of the parabola is another 2p units. So what's interesting about this is that if we know p, starting from the vertex, we could find the focus inside of the parabola. We could find the directrix on the outside of the parabola. And we could find two more points on the parabola that are 2p units away from the focus. We should recognize that this line segment is referred to as the lattice rectum. And these two endpoints of the lattice rectum will be 4p units apart, which should be interesting because remember how the coefficient called A is actually equal to 4p. So this coefficient of A, let's assume that A was 12, would indicate how far away the points are on this lattice rectum. And this is what's going to allow us to find all the information that we need to graph the parabola. So from the standard form of a parabola, we simply need to plot the vertex. Once we plot the vertex, we'll look to the coefficient of A and realize that A equals 4p, which will allow us to find this value of p that's so important to find the rest of the information. With p, we could then plot the focus on the inside of the parabola, the directrix on the outside of the parabola, and then we could find two more dots, two more points, which are the endpoints of the lattice rectum, which will then allow us to graph the final parabola with those 3 points. So let's take a look at an example then. Here we have our equation where y is being squared. So we should recognize that this is going to open left or right. Well, because the y value is squared and it opens left or right, we now just need to look at negative 12. Negative 12 is the a value, and since a is negative, the parabola must open left, and therefore I know that this is going to be the final shape of my parabola. Well, from here, we should be able to automatically see what our vertex is. Notice that the vertex is going to be positive 2 and negative 1. So I could plot my vertex at 2, negative 1. And because I know that it opens left and right, the axis of symmetry will be horizontal through the vertex, and therefore that's y equals negative 1. Now the next step is to find our focus. But remember, to find our focus, we're going to need to find the value of p. So remember that the a value of negative 12 is equal to 4p. So if 4p is negative 12, then the p value that we need is negative 3. Now, typically, we often think of the p value as being only positive to indicate a distance. But because we see that p is negative, that just tells me that the focus, since it's going to be opening left, is on the left side of the vertex. And therefore, we plot the vertex, or the focus, p units away from the vertex. So that point is going to be 3 units from the vertex, and therefore the focus is at the point negative 1, negative 1. Well, we should be able to now go on the opposite side of the focus to the other side of the vertex over here in order to recognize that the directrix will also be p units away from the vertex, only on the opposite side of where the focus is. So since this directrix is also 3 units away from the vertex, we know that the directrix will be the vertical line x equals 5. But we still only have 1 point on our parabola. So this is where we can now find the endpoints of the lattice rectum, recognizing that if I move parallel to the directrix through the focus, then I need to go 2p units up and 2p units down. Well, remember that 2p is simply 2 times 3 units, which really means that I'm moving 6 units up and down from the focus. So we can plot our new points, which are going to be -1, 5 and -1, -7. And once we have those, we can get rid of all the extra information and construct our parabola. And there it is. So notice that all we need are 3 points in order to draw our parabola. The most important point is the vertex, which we could find easily from the standard form of our parabola. But this A value tells us a drastic amount of information because it tells us what the values of P are that are necessary in order to find the focus, the directrix, and the endpoints of that lattice rectum.